Proof by mathematical induction example. Prove that 1 plus 1 over square root of 2 plus 1 over square root of 3 plus 1 over square root of 4 plus up to 1 over square root of n is always greater than 2 times square root of n plus 1 minus 1, assuming n is a positive integer. Okay, we're going to exercise a mathematical induction here. So like a domino, we need to start with first proof for basis step. So by basis step, we start from the smallest value of n. Because n is a positive integer, the smallest value can be 1. So the idea is if n equal to 1, then we want to see that p of 1 is true, or predicate corresponding to n equal to 1 is true. In that case, n is 1, so on the left-hand side of this inequality, we have just 1. So we have 1 over square root of 1 on the left-hand side. It should be greater than 2 times square root of 1 plus 1. I just replaced n with 1 minus 1. So let's check this. So this means on the left-hand side we have 1. On the right-hand side we have 2 times the square root of 2 minus 1. Easiest thing we can do is just multiply both sides of this inequality with a positive number, which is the square root of 2 plus 1. So we get, if we multiply both sides with the square root of 2 plus 1, we get and of course this corresponds to square root of 2 plus 1 greater than 2 times 2 minus 1, which means 2. So what we get is square root of 2 is greater than 1, which is always true. So basis step proven or proved. So next one is the inductive step, rest of the domino. So what are we trying to do here? In this case, let's assume predicate corresponding to n equal to k, where k is a positive integer, so k belongs to z plus, a positive integer, is true. Then we need to prove that p of n equal to k plus 1 is also true. So what is happening here? Well, we are saying p of k, which means this statement when n is equal to k is true. So we are saying 1 plus 1 over square root of 2 plus 1 over square root of 3 plus 1 over square root of 4 and so on, plus 1 over square root of n equal to k is greater than 2 times square root of k plus 1 minus 1. We are saying this is true. We are assuming this is true. This is referred to as Induction Hypothesis. So we make this assumption. Now we want to prove that p of k plus 1 is also true. What is p of k plus 1? It is 1 plus 1 over square root of 2 plus 1 over square root of 3 plus 1 over square root of 4 plus up to 1 over square root of k, and the last one is 1 over square root of k plus 1, because n is equal to k plus 1. So in this case n is k, in this case n is equal to k plus 1. We want to prove this is greater than 2 times square root of k plus 1 plus 1, which is plus 2 minus 1. So this needs to be proven. If you look at the left-hand side of this inequality, it's very similar to, so this left-hand side is very similar to the left-hand side of the induction hypothesis that we assumed is true. So what I'm going to do is, in order to get to this left-hand side, I'm going to add this additional component to both sides of the induction hypothesis. So adding 1 over the square root of k plus 1 to both sides of induction hypotheses what is the thing I'm going to get? Okay, so if I add 1 over square root of k plus 1 to both sides of this induction hypothesis, then on the left-hand side, I'm going to get what exists in the left-hand side of what I need to prove. So let me just refer to it as left-hand side. So I'm going to refer to this whole thing here as the left-hand side. And this is, of course, right-hand side. So with that in mind, I can say then, so with adding, what I get is left-hand side is greater than 2 times square root of k plus 1 minus 1, that is the right-hand side of induction hypothesis, plus the component that I added to both sides. Okay, so all I need to do now is I need to prove that this thing is still greater than 2 times square root of k plus 2 minus 1 here on the right hand side of what I need to prove, because I already know that left hand side from the induction hypothesis is greater than this guy. If I can prove this guy is greater than this, and then I'm done. So let's focus on this inequality supposed to be proven. So if I multiply both sides of this with square root of k plus 1, which is a positive number, not going to change if this is true. So if I do that, I'm going to get by the way, I can get rid of this 2 by dividing both sides by 2. So what I'm going to get is k plus 1 even before that, before multiplying, so let's divide both sides by 2, square root of k plus 1 minus 1 plus 1 over plus 0.5 square root of k plus 1 is supposed to be proven that it is greater than square root of k plus 2 minus 1. Well, these two cancel out. Now I can easily multiply both sides with square root of k plus 1. I get k plus 1 plus 0.5 should be greater than square root of k plus 2 k plus 1. Alright, then raise to the power of 2 both sides, so we get k plus 1.5 to the power 2 is greater than k squared plus 3k plus 2. Let's try this. So I get k squared plus 3 times k plus 1.5 to the power 2 greater than k squared plus 3 times k plus 2. Well, these all cancel out, and we are getting, of course, this thing is 2.25 is greater than 2, which is always true. So with this, we managed to prove the inductive step, meaning that from assumption that p of k is true, we can get to also p of k plus 1 through assuming k is a positive integer. So by mathematical induction, we just proved this inequality.